Like most training aircraft, the Piper Cherokee has a fixed pitch propeller. So what does that mean for it to have a fixed pitch propeller? Well, this blade angle doesn't change. You can look at the profile at which it's going to be cutting through the air. So the propeller turns down on the pilot's right side, it's looking in the direction that the plane turns. This propeller is going to be turning down in this way, so coming clockwise from this perspective. So this blade's going to be coming down and slicing into the air. And if you look at it, it looks a little bit like a wing. That's because it is. So this wing is going to be making lift in this direction, and we call that thrust. It's accelerating air backward, air is being accelerated backwards, and it's also pulling the plane forward, and that creates our force that it opposes drag. Now, this fixed pitch propeller, as you've probably heard thousands of times, is only good at one airspeed and one power setting combination. So this blade is going to be optimum to slice through the air at a certain angle, and that's about it. Anything faster, and we're losing efficiency because it'd be better to have a higher angle, and that would take a bigger bite out of the air, allow the engine to turn slower at a more efficient speed. Anything slower than the speed that this propeller is designed for, and we're losing efficiency because we have too big a blade angle. It'd be nice if we could have a slightly lower one to make better use of the air and not have sections of this blade stalled, just like our wings can stall. Or not even stalled, just at an unoptimal or overly excessive angle of attack on that airflow, just like a wing. One of the choices you have when ordering or adjusting one of these propellers is, do you want it optimized for cruise or climb? A climb propeller is great, and most training aircraft, especially these ones at our school, tend to have climb propellers, and that's because it allows us to take off in a decent amount of runway and climb safely. Too much of a cruise propeller, and it's very difficult to take off in the available runway. And then you get all the way to the end and you're not having a fun day. So it's nice to have a propeller that is going to be making good thrust for takeoff. And that's especially good for a flight school where we're doing a lot of takeoffs and landings. Now, if your goal is traveling around the country, now maybe you want more of a cruise propeller. But wouldn't it be nice if you could take off with a climb propeller and then switch it to a cruise propeller while you're in the air? That would give you the best of both worlds. If you are watching this video, you know that such a propeller does exist. It's called the constant speed propeller. And you can tell them apart from fixed pitch propellers because on the hub, it looks like it's a circle because this blade angle can change. The propeller can pivot on that pivot point way down in here. And if we can kind of see back inside there, that's a little bit better. You can see where it's really circular back in there. So that blade angle can shift to keep this propeller in an optimal range. So when you first go to full power for takeoff, the propeller will be like this in this low pitch. But as we add throttle, the governor will kick in, and we'll talk about the governor, and it will start adjusting the blade angle up, giving it a higher angle of attack, making it more efficient and protecting the engine from overspeed. Because if you compare this to the previous image of the fixed pitch propeller, this is even less of a blade angle than the fixed pitch propeller, because this is at the stop, at the low end of pitch or the high end of RPM. The other stop is somewhere higher up at a higher blade angle. So we're going to talk about how this works. If you're wondering what the governor looks like on these larger 6-cylinder airplanes, it usually hides right up under here. So that's the propeller governor there. When I was learning about the propeller governor for the first time and the way that a constant speed propeller actuates, I had a very hard time understanding exactly what's going on and what's working. For me, sometimes I need a physical model, and no one had that. So they say sometimes if you want something done right, you have to do it yourself. So here we go. This is a physical model of the propeller governor. It's not perfect. It's not exactly how the thing works, but it's close. It has 2 of the 3 major components and does a very good job, I think, of visualizing how it's all working. So before we get too deep into it, let's just go over the basic components here. This thing is built out of Legos. Legos are very, very fragile. So the real engine, the propeller hangs off the end of it. That's not possible with little plastic axles. That would sag and become extremely unstable. So what I have with this big structure back here, this is just structural reinforcements that hold the end of the propeller. But, you know, just pretend these aren't here. They're just there for this model to work. But this is simulating the engine. What I have on the end of it is a string that I can pull And what that will do is it drives some gears that are hiding back in here. I don't know if you can see those, but there's some gearing in there. So if this wheel turns slowly, this drive gear down here turns really fast. So I only have to move this a little and the propeller moves a lot. It just speeds things up. Okay, so we have random structure and engine established. Hopefully those make sense, at least from an airplane perspective. Airplane doesn't need these, airplane does need an engine. Now we can move into this section. From here to here, this is the actual propeller and governor. So here's our constant speed prop, and then this bit back here is the governor. The first thing that I like to show is this spring back in here. I couldn't find a spring that worked, but this tiny little spring in here, I had to get something, so I just twisted up a piece of wire that gives some springiness, and it does work. This is called the speeder spring, and this is a vocabulary word that you need to memorize and know. The speeder spring is very, very important on the governor because it allows everything to return to its starting position. So don't worry about these things yet, but when they spread out, that spring is what pushes them back to their proper position. See that? That spring is returning everything back to where it belongs. So tension on this spring is actually what you're controlling with the propeller lever. I don't have a propeller lever on this. I couldn't figure out a good way to get a mechanism in here. But just know, when you push the blue lever forward on your plane, what you're doing is you're pushing on that speeder spring, like this. So if I hold it still and I push on this little plate here, that increases tension on the spring. That's what happens when you push that prop lever full forward. You're putting a lot of tension on that spring. Moving on. Now we have these things. You can see that they hang loose, and I'm going to move this so I can turn it a little bit. There we go. So these are called the flyweights. They don't really fly, but they spin really fast. If they spin fast, centrifugal force pulls them out like this. If they spin slow, they come back together because of the speeder spring putting tension on them, on this plate here. See how there's a, well, maybe if I turn this a little bit more, you can kind of see in there. It's an L bracket. I'm not going to pull it apart, but you'll see that in diagrams, it's a little L-shaped bracket there. It has a weight up here, and then this little bracket that pushes on this pressure plate. And those little brackets push the pressure plate up when the flyweights move out. This is the one part on this that is not Lego, besides the spring and the string, there's some magnets in here just to give them more weight. The plastic was not heavy enough. I needed something with more substance to it. So far, this is exactly how the propeller governor on the real airplane works. You have a speeder spring that we can control the tension on with the prop lever, and we have flyweights. This is where the similarities mostly end, because I just mechanically connected it to the propeller. The real governor needs to be smaller than this. This governor here, this little model, is actually bigger than the real governor on the airplane. This is pretty big. The flyweights on the real airplane are probably half this size. So much smaller, and they need to be lightweight. And even with these huge weights, which are massive in comparison to what's on the real plane, they struggle to actuate this tiny propeller. So you can see the ratio of governor to propeller is ridiculous on this model. That's why the real airplane needs to do something to get this governor smaller. And the way it does that is it uses a valve and oil pressure. It's using a pilot valve is what it's called. And that's what this model is lacking. It does not have a pilot valve. So we'll have an explanation of how the pilot valve works along with the other governor components on the whiteboard here in a moment. But just know, we're using oil pressure to actuate the propeller blades on the real engine, but that's not really possible on a Lego model like this. I mean, I guess it would be, but I'm not an expert. I needed something that would help me understand the mechanism, and that's what this does. It accomplishes that quite well for me. I hope it can do that for you. So when these flyweights expand, they push on the pressure plate, and it's going to cause these propeller blades to rotate. So let me see if I can. I'm going to pull off this blade here just so I can change the angle a little bit. Nice thing about Lego is I can take it apart. Look at that blade angle there. We're sitting currently on the side of on the right side of the plane. So the propeller would spin in this direction on the real airplane. So I'll do that again. It spins in this direction, downwards on the right-hand blade. So the pilot is looking at the propeller from here. This is the front of the plane, this is the back of the plane. Engine, propeller, you get the idea. So as this blade comes down, you can see it's going to cut through the air. So as it rotates, it's going to grab some air and accelerate it backwards, and that's where some of our thrust comes from. If these flyweights expand, they will cause the blade angle to increase. See that? The blade angle gets bigger when the flyweights expand. I'm just spreading them out, and that blade angle gets bigger. It's going to take a bigger bite out of the air, accelerate more of it backwards, but it's also going to make more resistance. Think about it. If you have a fan that's really easy to turn, you're going to be able to turn it really fast. But if you have a fan that's hard to turn, it's going to be turning slower. Same thing on the airplanes. So we're just changing the resistance of the propeller blades on the engine. And this is where that concept of constant speed comes from. When the engine turns too fast, pull it here. When the engine turns too fast, the flyweights expand. The propeller blade angle gets bigger. The propeller takes a bigger bite out of the air, making more resistance, and that slows the engine down. When the engine slows down, the weights come back together, the blade angle decreases, and the engine speeds back up because now there's less resistance on it. And it'll sit there and it'll just fluctuate for a little bit until it finds the perfect blade angle that holds the speed that the pilot has selected. That is why it is called a constant speed propeller. This governor, with its just mechanical mechanism, is going to be trying to find a blade angle that holds whatever speed the pilot has asked of it. And how the pilot asks of it is just by changing the tension on this spring back here. More tension on the spring, it takes more speed for these weights to start spreading out and increasing the blade angle. Less tension on the spring, the propeller turns at a slower speed before it starts spreading out the blade angle, and now the engine slows down at a lower speed. So pulling the prop lever back loosens tension on the spring, pushing the prop lever forward tightens the spring, just like that right there. So I'm going to get this thing spinning and we'll see what happens. As I'm sure you saw, Legos have a huge limitation in that they don't really hold together too well. The propeller blades love to fly all over the place. So instead we'll have to remove them to really see these flyweights and speeder spring actuating. But just notice, as this thing spins, the flyweights, well, as the thing spins fast, the flyweights will expand, and then the thing will slow down, so the flyweights come back together. It'll speed up, they'll expand, it'll slow down, they'll come back together. That's what's happening in that governor. The engine turns too fast, the flyweights expand, propeller blade angle increases, engine slows down. And then the reverse is also true. So let's do a longer test where you can really see those flyweights doing their job. One way I have heard constant speed propellers described is like a manual transmission. So when I'm starting out, I'm here in first gear. The engine's turning fast, I'm making a lot of power, but it's not very efficient. So as I get faster, I can shift into a higher gear. This allows the engine to turn slower. I can't make quite as much power, but it's going to drastically improve the efficiency and life of the engine. A constant speed prop is a little bit like this, in that we're changing the ratio, in a way, of how the engine and propeller are interacting with the air. It's not a perfect one-to-one comparison. Another cool thing is I can downshift. I can go back down to first, get the RPMs up, and it helps with braking. It helps slow the car down. And you can do a similar thing with a constant speed propeller. By putting the propeller lever forward, that's like downshifting, going into a lower gear. It lets the engine make more power, but if you pull the throttle back, it's going to make more resistance, more drag, and that's going to help the plane slow down. So that's very helpful if you're flying a plane like a Mooney that's hard to slow down. It's one extra little trick you have to help bring the speed back down to where you need it, maybe before landing or something like that. So this is the typical diagram you will get of an engine and propeller governor. Well, really this, but we'll get to that part. Don't worry about that right now. For now, I've drawn out the engine of the airplane. On each side, you'll see that there are 2 cylinders, and there's 2 on the other side typically for these 200 horsepower Lycomings, at least what's in the Piper Arrow. But these governors are going to be the same, pretty much. They're going to work on the same principles at least. So we're just going to go over the principles of how the propeller governor, which is on the back of the engine for a Piper Arrow or a Mooney M20, how this thing is going to be actuating the propeller and changing that blade angle. Actually, if I move over here, You can see I've got it set up to where I can adjust the blade angle on this model or this drawing. So how is this actually happening? We use engine oil. It's already there in the engine, it's already circulating, and it does work as hydraulic fluid. So the crankshaft on just about any of these engines is hollow and it has little holes in it. The reason is there's a port up here so that oil can be injected into this crankshaft, and by sending oil into it, even though this whole thing is spinning, we can have a piston move in the front, in the propeller spinner section. And when that piston moves forward or backward, it can change the blade angle here. Now, the explanation I'm about to give is for a single engine airplane. Multi-engine is the opposite, at least in the way that oil is flowing and where the propeller will default to if it loses oil pressure. Just be aware of that. Let's start with single engine and then we can move on to multi-engine, or at least have a brief introduction to it, because I'm not a multi-engine instructor, at least not now. So the first thing I want to cover is the compressed nitrogen at the front of the spinner. Some systems I think use a spring, but at least with the Piper Arrow and most others, compressed gas, usually nitrogen, is quite commonly used. What this compressed gas is doing is it's putting a pressure on the piston. This compressed nitrogen wants that piston to move this way. So it's pushing on that piston inside this cylinder, and that's going to push the propeller to the lowest stop, kind of like we saw out in the hangar. When that blade angle is at its lowest, we can get maximum RPM. This is like first gear on my car. Okay, so we start adding some power to the engine. The RPM is going to increase, and then we're going to start getting into a point where the propeller is turning too fast, or it might overspeed. So what needs to happen is this blade angle needs to increase as we add throttle to prevent the engine from turning too quickly. Remember, this blade angle right here is a lot less than what it is even on a climb propeller for a fixed pitch. So we need to start increasing that blade angle as engine power increases to prevent it from turning too quickly. And the reason increasing the blade angle works to slow down the engine is the same reason increasing the angle of attack, pulling back on the yoke of an airplane, creates more lift. It's also going to make more drag. So the plane slows down when you pull back on the yoke. And this is where the constant speed aspect comes in. This blade angle is going to keep varying continuously until it fine-tunes and finds just the right angle for the speed and power setting of the engine to keep the RPM where it is set. So we're accelerating down the runway, we've put full throttle in, we need this blade angle to start increasing. So now let's move back to the governor. The governor is really small, so it's a pretty cool device that is this small and can actuate a pretty large propeller and have quite a significant change on the aircraft. And the way it does that is with this system over here. So we're just zooming in on the governor and kind of opening it up. This is simplified. This is not exactly how the governor is going to be working, but it's close. So what we have is a series of spinning weights. One are on pivots as well, so they can expand or spread out, or they can contract or come in. And that's going to allow this whole shaft here to move up or down. So we've added throttle, the engine's going to start speeding up. Now these flyweights are going to spread out. So let's draw that real quick. But see, these flyweights, as they're called, when they spin faster, the centrifugal force pulls them out. That's going to compress this spring. This is called the speeder spring. So we've compressed this spring as the engine speeds up. That pulls this valve this way. This is the pilot valve. And you can see there are a series of oil lines in here. The gears that drive the governor are also compressing oil. So we have engine oil being sucked into the governor, and it's acting just like a second oil pump. It's compressing that oil. Normally this valve is in the way, and we have a bunch of high pressure oil sitting here and kind of circulating. But, all right, it probably recirculates. I'm just simplifying the drawing here. Who knows? I'm not an expert on this. Because this valve has moved from its old position here backwards, you now see there's a path for the oil. So now this high pressure oil that's been accelerated by the oil pump that's inside the governor can move down this line. This oil is going to be at a very high pressure. It's going to move down this line. And when we get over here, this is the same line, by the way. I'm just drawing it a second time. So we have oil that moves this way. It's going to be pumped into the crankshaft. We have this nice high pressure oil. And now we have oil that has more pressure than the nitrogen. What that's going to do is it's going to push this piston backwards. and there are linkages or gears attached that allow the blade angle to increase with that piston. It's tied to the piston. So now the blade angle has increased. And you have felt this happen if you've ever flown a constant speed propeller. When you get it full throttle, you'll feel a surge for a second and you'll be pushed back in your seat. That's that blade angle finally increasing when the governor kicks in. And now we're starting to increase that blade angle and we're getting more bite out of the air. You're going to get a momentary increase in thrust, and that's what kicks you back in your seat as that governor starts to really start regulating the engine. As that blade angle increases, the engine speed is going to slow down. The flyweights are going to come back together. It's going to close off that line and stop oil flowing. Now, you might feel it kind of stutter for a second. It'll surge, the plane will surge forward, and then it'll slow back down. What's happening is there's sometimes a bit of a lag and an overshoot. So maybe this blade angle goes too much, and now your RPMs drop to 2,600. This engine and the arrow red lines at about 2,700 RPM. So if it goes too low, well, we need to push the blade angle back the other way. So now our propeller is turning too slowly. The centrifugal force decreases and the tension on this spring allows the flyweights to come back together because now they're turning too slow. The tension on the spring now overpowers them. This pushes the pilot valve the other way. And now we have a situation where the compressed nitrogen back at the front of the engine and propeller has more pressure than the oil because the oil in the engine is at a much lower pressure than what comes off of this oil pump right at the governor. So now that compressed nitrogen is going to push the cylinder back down. This line allows oil to move in both directions. That's why there's a risk of oil getting stuck in here, and it's why we do our propeller checks. It's one of the most important parts of the run-up on a constant speed propeller is because you don't want any oil to cool and get stuck in here. So when you do those propeller checks, prop forward, prop back, prop forward, prop back 3 times. What we're doing is we're really making sure we're unclogging this system. There are checks you want to do, but the main purpose of that is to make sure there's no clogs in here so that the engine doesn't overspeed on takeoff. That oil comes back down the line, and because this valve is open, it allows it to flow back through here and back into the engine. Once the engine finally finds its happy median, or the propeller finds its happy median, those flyweights finally move back to their neutral position. It blocks the flow of oil in either direction, and that nitrogen cylinder will equal out the pressure, so things will stop moving, the blade angle will stop changing, oil will stop flowing, everything just kind of stops. And that allows the engine to sit at the proper constant RPM. Of course, as soon as we push the nose down, get some airflow over the propeller, well, the engine's going to speed up. Flyweights spread out. We're going to open the valve. High pressure oil will go back down the line. It'll increase that blade angle. If we pull back on the yoke, slow the plane down, well, the flyweights are going to slow down. They're going to come together. Allow the valve to move the other direction. Now oil will move from the propeller back to the engine, and that will decrease the blade angle again. And you can see how this system will continuously vary until it finds the proper RPM. What is that proper RPM, you may ask? It's whatever you've set it to be. When we move this prop lever, what you're literally doing is you're changing the tension on this speeder spring. Prop forward pushes the speeder spring plate, or whatever this thing is that puts tension on the spring, forward. Prop lever backwards, I'll do this in a different color so you can see. We're going to be decreasing tension on the spring. And this will change where these flyweights are going to zero out, and that'll change the RPM of the engine. One emergency you might run into that is relatively common, and it's happened to me at least once, is a loss of oil pressure, possibly from an oil leak somewhere. So oil starts pouring out of the engine. That's not good, but we still need to have power somehow. At least this is the way the engineers are thinking. We want to make sure that we don't lose engine power. What would give us more power? Having the blade angle way out here at that stop, or way out here at this stop? This is going to give us more power. So that's why the nitrogen cylinder, oil leaving the propeller, will push it to a flat angle, low angle of attack, high RPM. Put differently, if we lose oil pressure, the nitrogen cylinder is dominant, and it will make sure that we have maximum available power. We'll have a low blade angle, high RPM possible when we lose oil pressure. This way, if you have a relatively common emergency of an oil leak, it will make sure that you at least have power available to do a go around a climb if you need to, and can hopefully get to the nearest airport. If it were the reverse, where loss of oil pressure would cause the propeller to do this, well, now a simple oil leak just became a full-blown engine failure, because this makes so much drag the engine won't be able to turn. And that's called a feathered position. Of course, single-engine airplanes don't fully feather. They maybe only go about this far on blade angle before they hit the high-end stop. But even that's a problem. That's a huge blade angle. You're not going to get a lot of power available. And that's where multi-engine comes in. Multi-engine, this is going to be reversed. Sending oil to the propeller will not increase the blade angle, it will decrease it, so that a loss of oil pressure will cause, because a loss of an engine on a multi-engine airplane is extremely dangerous. The drag from this propeller spinning will result in asymmetric thrust, which will try to roll the plane over. That's bad. So instead, the default for a multi-engine is for the blade angle to go here when oil pressure is lost. That way, you at least still have the other engine, and it helps control some of the thrust drag asymmetry, make the plane a little bit more controllable following an engine failure. So that's why single engine and multi-engine are different. It's just safety. Which one's safest for the given situation? On single engine, we want it to go here if we lose oil pressure. On multi-engine, we want it to go here if we lose oil pressure. So I hope you found that explanation helpful.